What we want to learn about in section 3.4 is how to find a derivative called the chain rule. So the chain rule applies when we have the composition of two functions. So as we see here, this is what we're trying to figure out, is the derivative of f of g of x. And so we're going to have to get good at learning to look at these functions and seeing them as functions inside of functions. So each of the three functions you see here, the blue, the green, and the yellow, are the composition of two functions. So f has a function 4x minus 3 that is inside the x to the fifth function. And the g of x has a function 5 minus 4x that is sitting inside the square root function. And h of x has the inside function x to the third plus 5x that's sitting inside the e to the x function. So part of the challenge here is to get skilled at identifying composition of functions. When we have an f of g of x, which function is the g of x and which function is the f of x? Because that's going to matter. Now, on top of that, we're going to get two different sets of words that we will use and two different sets of notation to explain or show or know how to find this derivative. And each one has its advantages and disadvantages in different situations. So it's really going to be important for you to get comfortable and competent with both sets of notations there. So here, the first one we're going to talk about is we are going to call this, we're going to say it's the derivative of the outside function, leave the inside function alone, times the derivative of the inside function. So I'm going to say that again. The derivative of f of g of x is the derivative of the outside function, leave the inside function alone, times the derivative of the inside function. Okay, the second notation that I'm going to use here is sometimes referred to as U notation. So it's going to sound and look different, but they still get us to the same place. So in this one, we imagine that we call the inside function, our g of x, we're going to call u of x, which we're going to refer to as just u. So then what happens is we convert our f of g of x into, and don't get your feelings hurt here, it's f of u. So we think of that as f of u. Now, then we use our Leibniz notation here, and we say the derivative of y with respect to x is going to be first the derivative of y with respect to u times the derivative of u with respect to x. So this is, again, this notation is having the same effect as taking the derivative of the outside function, leave the inside function alone, times the derivative of the inside function. But there are times where this notation is going to work just much more conveniently and make it much easier to communicate. Other times, it's going to help to be able to think of it the first way, as the derivative of the outside function, leave the inside function alone, times the derivative of the inside function. Okay, let's see if we can see how this works. So looking at that first one, we're going to say, now we need to see that the inside function is the 4x minus 3. That's the inside function. And the outside function is going to be the cube, the fifth root, the fifth power function. That's the x to the fifth. So we take the derivative of the outside function. We're going to bring the 5 in front, leave the inside alone to the fourth. Or that's also what we would call dy du. Think of this as u to the fifth. And so you're going to get 5u to the fourth, and then you're going to take that times the derivative, and actually what we'll usually write it as, instead of calling it du dx, we'll just call it du. So we can get 5 times 4x to the fourth, that's derivative of the outside function, leave the inside function alone, or the 5u to the fourth, and then times the derivative of the inside function is the derivative of 4x minus 3, or the derivative of u is that 4. So there is our chain rule derivative. We'll do a little minor cleanup and bring the 4 in front where it multiplies that 5 to become 20. And this is our derivative, 20 times 4x minus 3 to the 4th. Let's try the second one. So we're going to take, let me change my colors. So I'll go to green. So we have g prime of x. Now we want to think of that as 5 minus 4x to the 1/2 power. So we can either think of 5 minus 4x as the inside function and x to the 1/2 as the outside function, or we can think of the u as being 5 minus 4x, and so we can get the derivative of the outside function, leave the inside function alone, or the derivative of, if we think of that as u to the 1/2, then we're going to go 1/2 u to the negative 1/2, and then we're going to multiply by du, or we're going to multiply by that inside function, negative 4. So that's going to be negative 4 times 1/2 is negative 2, and you're welcome to either leave that as 5 minus 4x to the negative 1/2, that would be terrific, or at some point in time, we're going to want to be able to call that negative 2 over the square root of 5 minus 4x. So we want to be able to do it both ways. All right, here we go, h prime. So now what we get is this, a nice way to think of this is e to the u. Okay, hit the wrong button there, so I'm back. So a nice way to think of this is the derivative of e to the u is going to be e to the u du, especially with exponentials, and we'll learn shortly trig functions too, that u du notation is kind of nice. So we get e to the u, so we just leave that the same. That's the derivative of the outside function, of the outside function, sorry, e to the u. So you get e to the, leave the inside function alone, times the derivative of the inside function, or times du, which is 3x squared plus 5. And so not really much you can do with that. You can kind of leave it either way, actually. And it might be a little easier notationally because to write it this way, but they're pretty much equally acceptable. So there's our h prime of x. Okay, so let's bring this in with product and quotient rules. So I will say together with product and quotient rules. And when you're getting started here, sometimes people get confused, particularly with when to use product rule, when to use chain rule, and how to do them in the correct order. So let's take a look at, say, f of x is going to be, and we'll go 5x e to the x cubed. So there's our function. Now, what we have to train our eye to see is that we have a product of two functions, 5x and e to the x cubed. And that e to the x cubed is a chain rule because it's a function inside a function. The x to the third is sitting inside the e to the x. Okay, this is going to be fun. So we're going to get the first one, 5x, times the derivative of the second, and I like to think of e to the, this as e to the u. So we're going to get e to the u, the same thing back, times du, the derivative of that exponent, which was the inside function. So there's our first times the derivative of the second, plus the second, that's e to the x to the third, times the derivative of the first, and the derivative of 5x is just 5. So not really a whole lot we can do. We can bring this 3x squared in front to multiply that 5x and call that 15x to the third e to the x cubed plus 5e to the x cubed. Whew, this is serious stuff. Okay, let's try another one. Let's do g of x is going to be 2, let me pick a different one than one I'm going to do in class. Let's go 3x plus 2 to the fourth over 2x minus 7 to the fifth. And we're going to try to find g prime of x. So we have a quotient rule here, but then both the numerator and the denominator are composite functions and will require the chain rule. Whew. So we have the denominator, that's 2x minus 7 to the fifth, times the derivative of the numerator. Now the derivative of the numerator is going to be a chain rule. So we can think of this, if you like, as u to the fourth, and that's going to become 4u to the third times du, the derivative of the inside function. So that's going to be 4 times the u, which was the 3x plus 2 to the third, times the derivative of the inside function, the 3x, which is going to be 3. Wow. Denominator times derivative of the numerator minus the numerator, that's 3x plus 2 to the fourth, times the derivative of the denominator, that's going to be, here's another chain rule. So now we have a u to the fifth, so we're going to get 5u to the fourth times du, that derivative of that inside function. So that's going to be 5 times 2x minus 7 to the fourth, and then times the derivative of that inside function, the 2x minus 7, which is 2, all over the denominator squared. That's going to be 2x minus 7 to the fifth to the second is going to become the 10th. Wow. Well, now we have to do some serious simplification here. Okay, so this now is where it gets hard. The calculus is done, the algebra is just beginning. So we have two terms here. So we have all of this is one term, and all of this is the second term. So we're looking for common factors. So it appears that we have a 2 here, and there's a 2 in there. So I'm going to factor the 2 out of everything. Now we have a 2x minus 7 to the fifth and a 2x minus 7 to the fourth. So they have in common the smaller of those exponents. That's 2x minus 7 to the fourth. We have a 3x plus 2 to the third and a 3x plus 2 to the fourth. So they have in common the smaller of those exponents, the 3x plus 2 to the third. Now, what's left behind is what? Well, let's see, we took out the 2 out of the 4, but there's still a 2 left, and that 3 as well. So 2 times 3 makes that 6. Now we took out a 2x minus 7 to the fourth, but this was a 2x minus 7 to the fifth. There's still a 2x minus 7 that remains. We took out a 3x plus 2 to the third, and that takes care of all of that 3x plus 2 to the third. So that's it for the first term. Minus. Now the second term, we took out the 2, but the 5 remains, so it stays here. We took out a 2x minus 7 to the fourth, which accounts for all the 2x minus 7s here. So those are accounted for. We took out a 3x plus 2 to the third, but this had a 3x plus 2 to the fourth. There's still another 3x plus 2 that remains. That's all over the 2x minus 7 to the 10th. Is that right? Yes. So we can, it looks like, cancel 4 of those 2x minus 7s with 4 of those, leaving behind 6. So now I'm running out of space. So, and I hate to go to a new panel, but I think I can just move this up. Oh, look at there. I can create more space. That was pretty cool. So now what we have is we still have this 2. We have that 3x plus 2 to the third. Now we're going to clean up inside those brackets. And it's all going to be over the 2x minus 7 to the sixth that remains. Okay, so inside the brackets, we're going to distribute. 6 times 2x is 12x. 6 times negative 7 is a negative 42. Negative 5 times 3x is a negative 15x. Negative 5 times 2 is a minus 10. We're almost done. So this is going to be 2 times 3x plus 2 raised to the third. And now the 12x minus 15x is a negative 3x. The negative 42 minus 10 is a negative 52. and that's all over 2x minus 7 to the 6th. Well, I guess we can do a little bit more. 3 goes into 52, doesn't either. So if you want, you could factor the negative all the way out of that, but that's kind of just aesthetics. So you can stop right there, or you could bring that 2 all the way out in front and call that 3x plus 2 to the 3rd, and leave behind that positive 3x plus the 52, and all over the 2x minus 7 to the 6th. Whew. Okay. Well, let's see. Did I get all those? Let's go to a new panel here. Okay, and so let's see if we can do a crazy 3-link chain rule. These are tough. So we call these 3-link chains because there's going to be a function inside a function inside a function. So we have our f of x equals e to the, let's call this x cubed plus 4 squared. Whew. So I like to think of this as eating an M&M with peanuts. And so you start and you eat the candy coating on the outside first, leaving the chocolate and the peanut alone. Then once you've eaten all the candy coating off, you eat the chocolate part. That's the middle function, leaving the peanut alone. And then finally, you eat the peanut. So the idea is you work your way outside in. So we have here e to the u. And so we're going to first differentiate that e to the u, which is just e to the exact same thing back. Okay, so that's taking care of the e to the x part of this. Now we have an x cubed plus 4 to the 2nd. So that's a function inside a function. So we're going to think of that now as u squared. And so that will be 2u to the 1st times the du. So we're going to go now 2 times the x to the 3rd plus 4 to the 1st. And then times the du, the derivative of that inside function, which is a 3x squared. Wild and crazy. We can combine these, and so that can be 6x to the 2nd times x to the 3rd plus 4 to the 1st times e to the x cubed plus 4 to the 1st squared. Sorry. Okay? Crazy. All right. Let's maybe do one more of those. So let's do a 2 raised to the 3x plus 1 raised to the 4th power. So again, we're going to take this derivative. So we're going to differentiate this thing. So the outermost function is the 2 to the u. So we go, that's 2 to the, leave that exponent u alone, times here, because that's not base Euler's number, we have to multiply it by a natural log of 2. Now we're to the exponent part, the du, but that's a u to the 4th, so that's going to be a 4 times 3x plus 1 to the 3rd. And now finally we're to the derivative of the innermost one, the 3x plus 1, and that's going to be a 3. A little bit of cleanup. 3 times 4 is going to be 12. That's going to be 3x plus 1 to the 3rd times 2 to the 3x plus 1 to the 4th, and then tack on that natural log 2 at the end. Crazy, crazy. All right, I think we'll stop there. I changed my mind. Let's do one more tough problem here. So I'm going to split the screen here, and let's ask the question, for what values of x is the function f of x equals e to the negative x squared concave down? Wow. So what we need to determine concavity, to be concave down, we need to know where is the second derivative negative, which means, of course, we have to find the second derivative. Now, the first derivative is going to be a chain rule derivative because this is e to the u. And so its derivative is going to be e to the u du. So the same exponential back, e to the negative x squared, now times the derivative of the exponent, that's going to be a negative 2x. So I'm going to write this with the negative 2x in front, negative 2x e to the negative x squared. There's our f prime. Now we're going to boldly try to find the second derivative. But now I hope you can see we have a product of two functions, the negative 2x times the e to the negative x squared. So we have to do the product rule. So we'll get the first, negative 2x, times the derivative of the second, but that's our chain rule again. So that is again going to be e to the u times the derivative of the u, which is going to be a negative 2x. So far we have first times the derivative of the second, plus the second, that's the e to the negative x squared, times the derivative of the first, which is a negative 2. Now we're trying to figure out where is this equal to 0 so that we can then figure out where it's going to be negative. So now it has become a big algebra problem. So it looks like we have a common factor of negative 2 and also of negative x squared. So let's take out negative 2 e to the negative x squared and see what that leaves behind. So here in the first term here, we took out the negative 2, we took out the e to the negative x squared. We still have the x and times the negative 2x, so I believe that's going to be a negative 2x squared. And then everything came out here, so we have left only the plus 1, and that's still equal to 0. Now this looks daunting, but we can actually do this. So what we see happening here is we have two things that are multiplying to be 0. So one of those must be 0. Well, an exponential is always positive, and so this will never be 0, so we can ignore that entirely and now just focus our attention on what makes negative 2x squared plus 1 equal to 0. Well, we can add that 2x squared to the other side, divide by 2, square root both sides, and we want all possible square roots. So I'm going to make that square root of 1 over the square root of 2. Yes, we can rationalize that, but we don't really worry about that so much anymore. So now what we have is two places where that second derivative can be 0. We want to know where is that second derivative going to be negative so that we can determine if it's concave down. So we see there are two places where this second derivative can be equal to 0. So these are the only places where our second derivative can change sign. So now we're going to plug a number somewhere on the left region here. So I'm going to pick something like maybe negative 1. Now back in the original here, if we plug in negative 1, then e to the anything is a positive number times negative 2 is going to be negative. Negative 1 squared is positive 1. Positive 1 times negative 2 is negative 2. Negative 2 plus 1 is a negative, and a negative times a negative is positive. If we plug in something in the middle region, like say 0, e to the 0 is 1, times negative 2 is still negative. 0 squared is 0, times negative 2 is 0, plus 1 is now positive. A negative times a positive is negative. Plugging in a positive 1 means we're going to get e to the anything is positive times a negative 2 is still negative. And now plugging in a positive 1, we're going to get back to negative 2 plus 1, which is negative again, making the negative times negative positive. So to answer the question for what values of x is f of x concave down, it will be on that interval. You can either write it in interval notation as negative 1 over square root of 2 to positive 1 over square root of 2, or you can use inequality notation And notice that with concave up, concave down, we never include the endpoints. Ah, very good.